Man, I really should have picked a thicker. Tra-la-la.
Oh, hey, Miss T, what you doing over there?
Well, just 6.5. Interpreting and sketching giraffes.
Sketching giraffes? I thought 6.5 was... Wait a second. Did you cross out graphs and write giraffes?
No. Obviously, giraffes is in blue font, just as the rest of the title. Must have been a printer error.
You sure? Because it looks like you kind of just wrote it there.
I'm sure. But isn't Oliver cute?
Is Oliver the giraffe?
Yeah. Look at how cute he is. He's going to be our friend for the lesson. Speaking of lessons, let's learn some stuff.
Okay.
So we're going to be talking about graphs today. And graphs are actual visual or pictorial representations of how we relate two parameters together. Okay? There's different ways that we can show a relationship, and most often we do so using lines. Now, we can use straight lines, and straight lines represent a constant rate of change. In any sort of straight line, the steeper the slope of that line, the greater that rate of change is. The less steep that slope is, the, not greater, not least, lower that rate of change is. So, we're going to take a look at different types of lines that we can draw that indicate a change, like some sort of increase. So we just said that straight lines can represent a constant rate of change. If we want to show an increase, we can draw a straight line that would represent a constant increase. But straight lines aren't the only type of lines, right? We could have curvy lines. We can show a line like this. It still represents an increase because we can see that it's going up as we move from left to right. And even something like this could show an increase because the arrow is getting higher or pointing upwards as we move from left to right. All of those would show an increase. But this first one would be the only one showing a constant increase. The other ones, because they are not straight lines, would show a non-constant or a non-stant increase.
So since it increases going left to right, that's an increase. If the line falls as you draw it left to right, the change is a decrease. You really iron the lines, because when you iron, you decrease your clothing. I have jokes too. Anyways, so a falling line, I really didn't want that to be straight, but I guess I kind of did. But a falling line, and always read left to right. So if we fall as we're moving left to right, that's a decrease. And that is, of course, since it's a straight line, a constant change right there. But, again, it can change at different rates. So it could still be like that. That's still falling as you move left to right. Someone on their little sled going down this, whee, would still be falling the whole time. And that's still a decrease. But this one is not constant. And we could still even decrease like this. Woo! Oops, too many arrows. Someone have a really fun time being on their sled on that one. Zoom, zoom, zoom. But that is, again, not a constant rate of change.
If we know that increase in our rate of change occurs when our line rises, and a decrease occurs to the rate of change when our line falls, we can say that a horizontal line indicates that there's no change in the rate at all. So if we draw a straight horizontal line, that indicates there's no change in that rate. Alrighty, so we are going to just sum that up, is that the relationship is represented by a curve, any sort of non-straight line, then that is going to be a not constant rate of change. We're going to take a look at an example of a graph. In this particular graph, we can see that the relationship is between time and the distance from home. In this case, it's Noelle's distance from home. And what we can do is we can analyze the different segments of the graph. Just for clarity, I'm going to call this line segment here A. We'll call this next one here B, then C, then D, then E. Just so that we can talk about them and make sure that we all are on the same page here. But there's 5 different line segments here. One thing we might note is all of these line segments are straight. So what does that tell us about each of the rates at each of these points?
That's right. It's constant. I'm assuming that they said it's constant to their screens.
I heard it when they
Yes.
shouted it to me.
Yeah.
Yeah.
Any poops, we can label what's happening at each of these segments, or know what's happening at each of these segments now that they're nicely labeled. So if this is Noel's distance from home during a run specifically, so he's out for a run, what's happening at each of these points? Here, he's probably running. We could say that he is maybe running.
How do you know that he's running and not walking in that situation?
I'm feeling like this one's pretty steep. I'm not looking at this one on its own when I'm thinking that. I'm thinking the next one isn't quite flat, but it's a little bit flatter. So I'm thinking in this segment A, he's got to be going faster than in segment B. Do you know? Do you feel?
Je feel, je know, and je dig.
Now, as he goes on segment A, he's getting further and further away from home. So he must be running away. Poor little guy's running away from home.
But you know what? He's doing it at a constant speed. And we should indicate that so that we know that we're interpreting that graph as is.
So we've noted he's going at a constant speed.
Dang, Noel took a hit in his pace. Look at point B there.
Oof!
He was running, and then, maybe he's, that's pretty shallow in terms of the slope. So I would say maybe it's a walk. I would say at that point, you know what? He's still walking away from home, right? Because his distance from home is increasing. But I would say that he's probably walking away from the house at a constant speed at this point. I don't know what happened. Maybe he started to break a sweat and he's like, man, I don't want to get sweaty before I go on my run. Maybe he's running to a particular location.
Yeah.
You know?
Oh, but check what happened in part C. Look at that. He really picked up speed again. Woo! He's booking it.
Maybe he's just doing HIIT training. Gotta get them intervals in. Run real fast. Walk. Run real fast.
All about that interval grind. So yeah, I think he's actually just doing the same thing as he was in A. They look pretty identical. So does my text. And then, D. Gosh, what do you think happened?
My bet. Noel was running so fast.
Okay.
He stepped on a banana peel, flipped,
Yikes.
fell, didn't injure himself, but it was hilarious. And then that's why his distance from home stopped, right? He wasn't getting any further from home, and he wasn't getting any closer to home, so that horizontal line representing no change must mean he stayed in place. So I think Noel tripped, he fell, he's not moving. Took him a couple seconds to maybe stand up, dust himself off, look around awkwardly, make sure no one saw. But that's what I'm thinking's happening. So no change. He's not moving.
I like to think that he kind of just saw a really cute puppy.
Oh, and he pet it.
And he just kind of stopped there for a bit. Like, you know what? Why am I out for this run when there's puppies in this world? And I'm just going to stop and pet this puppy for a bit.
You know what? That would probably explain E, because Noel actually got a puppy of his own. So
Yeah.
It looks like in E, he's already headed back home. So maybe he saw that puppy and he's like, oh my gosh, I missed my puppy. So he decided to turn around. We noticed that the slope for E is not as steep as it was in A and C. but it's not as flat as it was in B. So it's kind of got to be in between running and walking. So we could say jogging. Actually, you already said jogging. But yeah, we could say jogging so that we can indicate the different speed in relation to those different slopes.
I just said jogging because I assumed he was wearing joggers. Isn't that what you do when you wear joggers? So we have another example.
And in this example, we're going to be talking about different graphs that exist and which one would best represent a particular situation. And in this case, we're looking at an athlete's oxygen requirements over the course of an exercise from warm-up to cool-down. So we're trying to figure out which one of these graphs, A, B, C, D, or E, would best represent that. Some assumptions that we might have, I don't know, maybe you've worked out once in your life, or at least once, is that as you work out, you take in more oxygen the harder you work. Right? Like, I don't know, maybe if you've gone on some sort of run, you're jogging, and jogging. I know I could have used running, but
No.
Anywho, you're jogging, and all of a sudden you notice that your breathing's getting heavier, right? The whole reason that's happening, science tidbit, is that your body needs to get more oxygen to your blood cells so that you have more energy and things like that. So with that being said, you need to breathe in that oxygen, and then your heart is pumping that blood around more quickly, so you're taking in more oxygen. As you're warming up, well, think about it. You're slowly going from a normal oxygen intake to an increasing oxygen intake. So we should be looking at the beginning of these graphs to at least be going up. This one starts to go up here. This one's staying kind of flat, so I question B altogether. This one's staying flat and then dropping, so I think I'm just going to cross out C right away. This one here, I could see that there's an increase, and this one here, I could see there's an increase. Now, over the course of your workout, your oxygen intake remains fairly high, right? Think about if you're going for a run. You're not necessarily breathing really heavily at the very end and very lightly at the beginning. If you're kind of in the midst of your workout, say you're going on a half-hour jog, first of all, impressive as heck. But second of all, your breathing during that kind of 30-minute run period, assuming you've warmed up beforehand, is fairly constant. So we should see something like a no change in that oxygen intake level in somewhere in the middle of our workout. And so here I can see it keeps on increasing. That would be a health concern, and for those reasons, I'm out. It's like Shark Tank now. Here I could see that it's staying pretty constant. I'm still a little bit skeptical in the fact that my O2 intake didn't really increase over the beginning, but maybe I started off just came into my workout already having warmed up. Questionable, but fine. But here I can see this is pretty constant, so that's pretty dope. Here I can see this is increasing at this point, and for those reasons, I'm out to go see a doctor. The last portion of my workout is a cool down, right? I'm slowing how fast I'm working out, which means I'm also probably lowering my oxygen intake. I'm not breathing as heavily. I'm kind of getting back to that normal pace. So my breathing and my oxygen intake should decrease. Looking at graph B here, I can see that it keeps increasing. Again, at this point, call your doctor, make sure that you're okay. But D looks like that decrease is occurring. We can see that in graph D, this would be the one that best depicts our situation. But we can see that here we have the increase being non-constant because it is not a straight line, which is pretty typical. My breathing is continuous, and it's just slowly going to increase and increase and increase until it reaches that kind of high level while I'm working out, and then it's going to slowly decrease and decrease and decrease as I get back to my cool down. So just to kind of sum up some of that information here, we could say, well, my warm up has an increase. My grind is fairly constant, right? I'm not really expecting much change. And then my cooldown, that's not how you spell cool. I was thinking close for whatever reason.
Cool.
My cooldown, I'm going to see a decrease in my oxygen intake. And this is exactly what graph D depicts.
In our last example, Kelly, hey, that's my brother-in-law. He throws a bouncy ball high up in the air.
Whee!
Whee! It goes up, and then it comes down. That's what happens. You throw things up, and then they come back down. But it's a bouncy ball. So it hits the ground, and then it goes up again, but not as high, right? The energy goes somewhere, probably into the floor.
Not an elastic collision, am I right?
Classic. And then it's just going to keep bouncing and bouncing and bouncing until it stops eventually. So, little question. What might the graph of this ball's height above the ground over time look like? Give it a try, I triple dare you.
Ooh.
Yeah, that's high level dares right there. I'm assuming you've tried things. I'm going to draw some stuff. When I kick this off, I'm going to draw some axes. Now, time is always positive, and the ball's height, it wouldn't make sense to go into the negative land, so I don't really need this area here. We're just going to have that top stuff going that way, going that way. The axis continues, but we don't really need those areas. I'm going to say that the height is a dependent factor. So it'll be like our y-axis, but it's our height axis. And then time is our independent parameter. So that will be there. And this is a graph of the bouncy ball height over time. So the ball starts at some height. What height? I don't know. But Kelly does something with it. He throws it up in the air. So it goes up in the air. It goes up, it comes down. So that's going to be that it goes up, but it doesn't like suddenly come down. Whenever you throw a ball, you notice that it kind of just gradually says, oh, you know what, I've reached my peak height and now I'm going to fall. The end. Ball's done. It's not doing anything. Psych! It hits the ground. It goes up again. Just not as high as it did before. So it hits the ground. It goes up again. Whee! It goes boing. But just not as high. It doesn't quite go. It just doesn't make it. So then it comes back down again. And we're going to see that repeat. It's going to go up a bit, but just not as high. Oh, it tried. And then it came back down. And then it bounced, went up in the air, and it came back down. It went in the air, it came back down. It went in the air, it came back down. Oh, it tried. It just couldn't go up anymore, and then it just rolled. And that's the graph of the bouncy ball over time. It's a little rough. I mean, it's not as precise as it could be, but we're just sketching the graph. It doesn't really need to be exact. Do you know? Do you feel? Do you dig?
You dig, you feel, and you know.
In that order?
Yeah, actually, that's pretty accurate.
Nice! Special news. This is a brand new announcement that you've probably never heard before, but check this out. We've got some practice work here.
Ooh.
Right? Brand new feature to these videos. I think it's pretty wicked.
Yeah.
Some might even say wicked cool. Or wicked dope. Whatever you're feeling. So, recommend giving that a shot, giving it a spin, giving it a whirl, giving it a try, giving it a go, giving it an attempt.
You can do it all, and we believe in you. And you know what? Oliver believes in you. And with that, we say goodbye.
How does a giraffe say goodbye?
I have no idea what kind of noises giraffes make.
Apparently a pterodactyl noise is what they make. That's